Okay, so good afternoon, everyone. Hopefully, everyone enjoyed their academic break from last week. I also took a break for an entire week for personal matters. But now that we're back to our regular programming. So hopefully, everyone got to read my email a while ago, wherein I mentioned that we'll have our sync session again today. We'll have an async session sometime Wednesday, and then we'll have another problem set on Thursday. Okay, and then it's the same thing. We'll try the same thing we did the last time. We're in around 3 days to complete the entire problem set. Although this particular problem set will be special because it's actually divided into two. The first part will be trying to come up with your own solution to a certain problem that has already been solved, that is already optimal. So what I'm talking about are actually hash functions. So hash functions are relatively solved already, and if you could find a better hash function, then you wouldn't really need to work anymore because there's a price for that. But it's just a good academic exercise just to get the concept across. And then the second part will be our usual problem solving. So there will be I think 3 items for this week that will involve graphs. Okay, so that's what we'll mainly focus on now. And then in the other announcements, the topics part for the sign up list, I forgot to mention in the email. The topics part in the sign up list. So hang on, let me just pull that up. Okay. So the topics part, oh, not that. Okay, so this one. So you're not to fill this up. So this one is for me to take note of what each group is currently working on. Okay, so it's not the title of your paper. So I've seen some people changing this, but I guess I should have recorded it offline. But I also posted this here so that other people can see what other people are doing, so that you can maybe share some insights with other groups that are doing a similar sort of problem. Okay, but in any case, the topic part is for me to fill up. And then those who are already approved, again, you can move to the second checkpoint. So please put in your details here and wait for me to confirm. I'll send an updated email for those who have confirmed schedules. But again, you can't jump to the next part without completing sort of the first checkpoint or milestone. Right? Okay. So yeah, so that's for the announcements part. So for today, we'll actually be going through two slide sets. I already uploaded them on uh, on on Canvas, and the first one is rather just short because again this is already a solved problem, so not much problems we can actually apply to it to practice it because almost every programming language already implements an optimal hash function. So for the most part, we'll be focusing on graphs. So the graphs part is splitted into two parts. Part one will be discussed today, and then part two will be discussed on Wednesday, in the async part, because we need to make sure that we have a good understanding of what graphs are, how do we implement a very basic graph programmatically, and what are sort of the things we can do with a certain graph. Okay, so I'll just go to the hashes part first. Sorry, but before I do that, there's for those looking for or work on thesis, and this has been pushed a while actually for a few years now. Uh, the okay, so what's the narrative? Oh yeah, okay. So for those looking for a thesis for their graduate studies, one thing that's in right now, and one thing that's being pushed by university as well as other universities in the country and abroad, is to create an interdisciplinary study. Okay, so or interdisciplinary thesis or work. Right? So this means that you have the computer science people pairing up with the humanities, so sciences and humanities, or humanities and social, the social schools, SOSS in the case of Ateneo, so social studies, and then you of course have management. Okay, so a lot has tried to do a good interdisciplinary study, although I haven't seen one that was quite sort of groundbreaking. Uh, Consequently, the groundbreaking ones, or the good ones I consider good ones, come from the humanities department. So you have the people from ID. So if you're friends with people from ID, information design, they have this sort of session similar to computer science, where during intermission they talk about their topic and then how they want to involve other studies with it. So usually the pair is information design and computer science. So I'd like to share an article with everyone. This one was shared by my friend. It's very interesting read, but it's more of a social study rather than a computer science study. Now it's quite long, so I'm not requiring you to read it, but it's something worth exploring, especially if you're into things like politics, social justice, religion, and so on. Now, this one is very applicable to those familiar with Western politics. So the Reds versus the Blues, which is quite um, popular these days, right? With the whole politics in America going on. But the reason why I'm sharing this is because, regardless of it being a social study, there is actually room for computer science. So, for example, it talks about virtue signaling, right? So a rough definition of virtue signaling is that, let's say there's a point of view or a narrative. Let's say, just for example's sake, like people should get into sciences because that's the sort of the modern era course that everyone should take moving forward to the future. But then not many people can afford, going into the sciences. For example, in computer science in particular, although computer science is a it doesn't require a computer to use computer science. In most days, you really need a computer to perform computation. Like in machine learning, you need a very powerful computer to perform computation, and not many people can afford that. So the idea there is that you have different experiences from different people. That the narrative of saying that people should incorporate sciences throughout their careers isn't as black and white as saying as that happening. Meaning it's not as simple as saying, okay, let's incorporate science into our careers. So in short, the experiences of different people, you can think of them as weights, in an objective perspective. The experiences of different people can be sort of measured, right? Given a certain narrative, if I experience things differently from you, then the relevance of what I say might be different from you as well. Now that opens up a lot of social arguments wherein, okay, so does that mean I don't have the right to sort of give my opinion towards a certain political standpoint, right? And maybe if you can trace sort of where I'm going here, I'm talking in very abstract matters, but it might be very relevant for today's political landscape, especially with the elections coming in. So, the idea there is that the social studies, being a subject that has been known to be quite qualitative, because you're giving arguments that say, okay, this is the narrative and this is what I should follow based on existing studies. You sort of want to make it more objective. Although social sciences already do that with their surveys and statistical subjects, but in a computer science perspective, you can actually insert some sort of um, logical arguments to it, like give actual values. For example, they talk about percentages if you're a liberal versus a conservative, and what that actually means in terms of how you might contribute to a certain narrative, or if what you say is actually useless. In the case of virtual signaling, um, is it really because of your experiences? Is it just some? Is it really providing purpose to your life and to other people, or is it just noise? Okay, do you actually give a measure to that? So it's a very interesting article. So I'll share this with. I'll also post this on Canvas. I just read this earlier today, but it's worth looking at, especially if you want to mix philosophy, so the humanities, and social sciences with your thesis. And it's quite a challenge, and hopefully um, you might be able to come up, I don't know, with an algorithm for it, like a universal algorithm for it, or universal theory at the very least. Okay. All right. So enough commercial. Let's go now to our actual proper lesson proper. Okay. Mm, okay. 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 Sorry. Before I discuss the lesson, are there any questions or clarification so far? Good. All right. So again, for those who didn't sign up yet, please find the time to sign up for the schedule. We need to cross 3 checkpoints before we uh, produce the final project. All right. So let's first talk about hash functions. Okay. So what are hash functions? So meme of the day. If you don't need to have to download 1,000 images if the meme is cached once. So the idea there is that hash functions or hash tables in particular later on is sort of a hack in order for you to operate more efficiently in fetching information. So far we talked about searching, we talked about runtime analysis, divide and conquer, all of which have to do something about fetching some piece of information, right? And the idea for hash functions and hash tables later on is that you want to have some sort of cache, okay, or not cache, but you have to have some sort of storage mechanism that will allow you to reference a piece of information immediately without having to search it always from source. Now, an easier way to think about this is that you don't have to keep hitting your database in order to display certain results. So, for example, if you're working on a stock trading application, the stock trading application, the data for the price of a certain stock or asset is stored in the database. But the database, just like any other computer, is a server that does other things aside from storing data. Maybe you are updating the information of the stock at any given second or at any given minute. So you're performing an insert aside from performing a read. So the idea there is that with the amounts of data that is stored, if people have different needs of fetching different types of information, it might be better to use a cache or another mechanism that will only perform reads for existing information. Okay? And it operates faster, relatively faster, than always reading stuff from the database. Because that way, especially for historical data, you can expect that this data will never change. They're static, they're never changing, so you can easily read from them. Okay? Now, given that thought, we'll just go through the 4 most basic concepts of hashes, mainly the hash tables, hash functions, collisions, and load factors. So let's first talk about the relevance of hashes and the data structure of hashes. So the most common example is that you have a buyer asking for the price of a certain product from the seller. So let's say you're going to a grocery store, you'd like to ask how much are apples, milk, and chicken, and the seller has the item price. Now, the seller, the manager, for example, of the grocery store, will have to wait for your query. For example, the buyer asks, how much for chicken? So the seller then goes through each item list. Is the first item chicken? No. Second, no. And then finally, it goes to the third item, chicken. And then it replies, okay, it's 80 pesos. Now, the problem with that is that, again, even if the manager performs, is knowledgeable with computer science, even if the manager performs like a binary search for getting the actual price, it's still much faster if you know already beforehand the actual price. So what the manager could do, what the seller could do, is the seller could probably talk to his or her main employee, employee of the month, for example, and say, hey employee, please tell me how much chicken is. Now the employee knows where exactly chicken can be found. It's the third item on the list. So the employee already returns the price, and then the seller then returns the price back to the buyer. Now, it's a very simple situation, but that essentially is what hash tables or hash functions can do for us. They are a way to associate pieces of information using a certain index without having to traverse the entire list to look for that index. And the employee part is actually important because the hash table is separate from the actual, from the manager, or in our case, the program, performing the actual search. Okay, so you have a separate entity that will hold, that will know the information from the manager who actually owns the source material, which is the price list of certain products. Okay. Now, this is a very, of course, it's a very high level concept, and it's often taken for granted, especially when we go into programming, because hash functions, or identifying pieces of information with a certain index that you define, it's usually a string, is already implemented within the language. So, for example, in Python, you have the concept of dictionaries. In the case of PHP, they call it associative arrays. In the case of Java, they call it hash lists. Right? But the idea is the same. You are implementing what you call a hash function. So a hash function is a function that accepts a string and returns a value, or in other words, it maps that string key to a set of numbers. Now, you can consider a function to be a hash function if it satisfies the following properties. First, it needs to be consistent, meaning the index, which is the string key that you supply to your hash function, will always return the same number or value regardless of the call. So, for example, if we go back to this slide, if the buyer is looking for the price of chicken, it will always return 80. Yeah, simplest terms, right? So the key becomes the item you are actually looking for, and you are referencing that to fetch a specific piece of information called 80. Okay? Same goes for milk, for apples. They uniquely identify a piece of information without necessarily following a specific or without necessarily following a strict system like what you would have with arrays. Okay, so earlier in our arrays, we are only accessing information, the values inside the container of the arrays using the arrays index, wherein you have a fixed sort of you have a fixed size, right, for a given array, unless you use linked lists. But then linked lists are also strict, right? A linked list can grow or can shrink. It's dynamic, and we already went through the discussion of how it looks for certain items, because your element is linked to another element. It is a pointer or reference to another element, but it suffers from having to traverse the entire list if you want to search for something. Okay? In the case of hash functions, it always has to be consistent, meaning the index will always return the same number and value regardless of the call. Okay? And it should map different words to different numbers. So you are assured that the index that you are using is unique within that hash function. Every word should map to a different number, and it can handle proper collisions. Okay, so we'll talk about collisions next, but what the properties are essentially saying is that if you perform an insert, it should be O of 1, exactly one operation. And we can actually do this with linked lists, right? In linked lists, we simply add to the end of the list. And the search as well should be O of 1, which is something that you can't often have with linked lists, but you can have it with arrays, right? Because you know the formula of the index. But again, arrays suffers from structure because the arrays have a fixed size in memory. Okay? And it's also O of 1 in terms of removing that item. Okay? Now, the removing part is quite complicated, because if you say that you have a hash, let's just represent this by a star, for example. Okay? And then the star will have to access a key, so let's say chicken. Okay? What do you actually mean by removing? Well, if you want to make it O of 1, then removing can simply be, okay, given the string chicken, you are nullifying it. So you'll actually set this to null. Okay. Then you essentially remove the item from the hash, right? Because now chicken is pointing to nothing. You might replace it with something else, but if you want to remove it, you just have to point it to null, so it's pointing to nothing. So technically, it's O of 1. Okay? But if you think about it, this one still consumes some information, depending on your implementation, of course. But the hash function should be adaptable to that. Meaning to say, if I nullify chicken, then in memory, in my computer, I should also remove the reference to chicken. If I redeclare it again, then if I can fill in a new value, I have to create another key called chicken. It still should operate at O of 1 speed. Okay? So strictly speaking, hash functions are efficient, or more efficient than using arrays to structure information, because the main operations that you would do is at O of 1 speed. All right, questions first so far about this? Clarifications? All right. Okay, so a hash function cannot do away without a hash table. Okay, so what is a hash table? A hash table is an associative array. So it's the same term used by the PHP language, that the hash function references to return a value unique to a given key. Okay. So let's take a look at the example without minding the collision chaining first. Let's say that our hash function will use a table. So just think of it as an array, wherein the rules of the hash function is that I will get a value inside that array, okay, and associate it with a key. If my key is starting with letter A, then I will use slot 0. Okay, and then I will have my value inside that together with the key A. Okay, so for example, if I want to insert apples, I will use apples as a reference to this container, and in this container, I will have my value. So let's say 80 pesos. Okay. So that's good. I have a structure that can easily reference a slot with the value that I'm looking for. So it still follows the same properties. Inserting it is sure because I can model this after the alphabet, right? I can model this from 0 all the way until 26, or 25 rather, because 20. How many letters are there in the alphabet? 26. Okay. So I can model it all the way from 20 to 25, so 0 until 25. And that all keys, the rules of my hash function is that all keys that start with the letter A or lowercase a, and that's okay regardless, right? I can have a rule that says regardless of uppercase or lowercase, use slot 0. So in this case, my hash table already has a fixed size of 26. Okay, at the same time, I already know at which point at which container can I fetch the piece of information if I pass a string as my index with a starting letter. Okay, I'm using the starting letter of my key to determine the position of the value inside my hash table. Okay. Now, the problem with this rule is that, and why it's a terrible hash function, is that we're just simply basing it on the first letter. And we know that there might be other keys. For example, in this example, you have avocado, which also starts with the letter A, which, according to our system, will have to be stored in slot 0 as well. Okay. By the way, can you see the stuff I'm drawing on the screen via Zoom? Okay. I thought sometimes it's not showing. All right, so this is what we refer to as a collision. So essentially, a collision happens where the rules of your hash function, or how you associate a key to a certain value, will apply for other keys, even if they have different key values, or they have different spelling, so to speak, right? Apples is different from avocado, but because of their starting letter, okay, uh, they fall under the same slot. Okay, they have to use the same slot. Okay, so I can put here 80 and so on. That's what we refer to as collision. Okay? Your key, the associated key, follows the same rules as other keys existing inside your hash table. Now, what's a sort of solution to solve that? The easiest solution is to perform a process called collision chaining. The collision chaining is quite a simple idea. The idea there is that given the same rules, you have a collision. Whatever that slot is in the array that has that collision will become a list in its own respect. Okay, it can be a linked list, or most likely it can be a linked list. Okay, so that each element inside it will actually be a pair of the key and the actual value. Okay. So avocado might cost something else, so let's say 70, and afritada might cost something else, let's say 100. All of which follow the same rules. Okay, they are starting with letter A, and thus they belong to the same slot inside your hash table. Okay. This solves our problem in terms of avoiding collision, but why would you consider it a terrible hash function? Just as a mental exercise, who can tell me why this is still a terrible hash function, even if I can associate different keys for different values, okay, and at the same time, collision chaining allows me to avoid collision? Anyone? Why is this considered a terrible hash function? Based on how we defined hash function so far. Who can try to explain why this is a terrible hash function? Anyone? Okay, try to connect it with the grocery list scenario again. I'm trying to look for the price of a certain item, and I am using the key, a string, to reference that piece of information. Apples 80 pesos, avocado 70. But if this was our system, okay, wherein our hash function accepts a string, takes the first letter of the string, and then associates that with a container in the with a container inside the array, inside our hash table, we then have a collision. Okay? So we can avoid that by creating a collision chain, okay, wherein the element becomes a list of the same rules of the values. Okay, so we have an answer here by Caleb. Searching it won't be O of 1. Okay, so that's the simplest answer, right? If I wanted to search for avocado, then I can reference, if I pass to my hash function, I say hash avocado, I would go to the same container because it follows the same rules, but it goes against the properties of having a search that is O of 1. Now my search is not O of 1. I'm O of 1 when it comes to looking for the position in the array, but I am not O of 1 when it comes to looking for the actual value inside that sublist within it. So you're actually having like an O of n at worst, right? Or you can even do O of log n, but yet collision chaining will actually force your system, at least in terms of search, to be at worst O of n, or sometimes at best O of log n. Okay? So we consider this a terrible hash function. Okay. Right. Okay. Hopefully everyone got that part right. Now collision is the big problem in terms of hash functions, right? It's been the first the sort of one of the first problems that have been that computer scientists tried to solve when they created hash functions. Now, just to prepare you for the problem set on this coming week, who could give describe a good hash function Okay, algorithmically describe a good hash function that would still share these same properties. Sorry, these same properties. Okay. Actually, the insert and remove part has no problem. Okay, it's just that the search part is the problematic one when it comes to hash functions. Okay. How would you create a function that would be O of 1, wherein I get to store a key inside an array and associate that the container, the position of that array, using a key? Okay. The example we gave is that we start off with the first letter of the key, okay, and then use that as information for where exactly in the array can I find this slot for extracting the value. Okay. So just to exercise sort of our creative brains, who could give us made up made up hash function that seems to satisfy the properties discussed earlier? Because apparently alphabetical order doesn't. And keep in mind, you want to avoid collision. To sort of drive this mental exercise as well, try to think of it also in terms of the size of the array. Okay, because later on we'll talk about hash tables shrinking and growing when you use queues later on. In terms of the memory it consumes, how would you make a rule, or who can give me a rule that sort of satisfies the properties explained here earlier? Anyone care to try? I'll give you some time to think about it, a few minutes. I'll just get some water. But try to think about it. What is a good rule, aside from something as very rudimentary as selecting the first letter and using that as the means of creating my slots? Also, by the way, it's the user who defines the key. Right? So the user can say apples, the user should say avocado, and essentially what you want is something like, if I were to have a container, I want to really have apples and avocado as my reference. Or give another rule. It doesn't have to be a good rule. Give another rule and then say why it's not a good rule. Yeah, it's a good mental exercise. Yeah, I think that could be an easier thing to think about. Draw something here first. Anyone?
Sir, why not store just the actual key on the array?
Yes, so that's the misconception, right? If we do it in programming, it's very easy because we can store the key inside the sort of array. We create associative array and then we get a value. But if you think about it, how does the computer actually perform O of 1 if I take apples and put it there? Because this is what you just described, right? You store the key, apples, avocados, as the point in memory. But if you think about it, if I wanted to retrieve the price of apples, I will still have to perform a search. Okay, there has to be some rule to tell the computer that apples can be found here, avocado can be found here. Right? We know that's how it behaves, right? Because we use the key. But again, a hash function isn't as simple as declaring a key. The system has to have a rule, such as this very rudimentary system, like using alphabetical order to create the different slots so that I know A is 0, B is 1, C is 2, and D is 3. Okay, I'll try to give you another example and then tell me why it's bad. Okay? What if I use the length of a certain string, okay, as the means to define at what slot of an array am I fetching the value from? Okay, so let's say apples versus avocado. How many, if I use that rule, right? Again, the rule is I get the length of the string, okay, and then so I get an integer as a result. The integer value becomes the address of the array, essentially. So for example, apples has 1, 2, 3, 4, 5, 6 letters. Avocado is 1, 2, 3, 4, 5, 6, 7. 7? Yes, 7 letters. So I know that at position 6, apples will have a value, and then at position 7 or at index 7, avocado will have a value. So in that particular rule, why is it a bad function? Why is it considered a bad hash function? I can still perform O of 1 search, right? Or what is the collision in that case? If that was my rule.
So divide would collide with the same words with the same length.
Okay, so it would collide with the same words with the same length. If I have another word with the same length, then I would have to create a collision chain, right, for that slot. So if you can give me a word with 6 letters, let's say, think of cherry, Cherry. Yeah, cherry. So if I had another word, let's say cherry, as my key, I would have to create a collision chain. 1, 2, 3, 4, 5, 6, right? For that slot in the array. And then within it, the reason why it's also bad is because within it, okay, so yeah, so I removed it. Sorry, let's do this in Excel. Okay. Let's just say that this is our sort of slot array, right? So if we had apples here, we might also have cherry. So let's label this first. 0, 1, 2. Okay. Apples, cherry. Okay. So if our rule of length is it shouldn't be here. It should be 3, 4, 5, 6. Okay. So apples and cherry appears here, right? This is a good collision function only to the point that even if I perform a search here, I can still perform O of 1 in terms of searching because I know that if given a key, apples or cherry, I can go to slot number 6. I have a collision chain. So from there, I can then search for something. Okay, apples versus cherry, maybe I can assume that they're already alphabetical. So at the very least, I know where something resides in. But again, I go back to my original problem. I will still have to perform a search that is not O of 1. Okay. Right. So Kleb here says, does a hash function require to only have one key in that storage? Not necessarily, actually. Not necessarily. You could still perform a collision chain. That's why collision chains are still a valid solution for collisions, but it still depends on your mode of fetching. Because maybe if you had another sort of pseudo hash table here, and that one in turn is O of 1 in terms of searching, then you still satisfy the properties of a good hash function. Okay, so that's one example. Who can give me another example? Again, it's very hard because it's already a solved problem, right? You actually see this in for those of you who did like database encryption, you sort of, the algorithm used to encrypt or to create a hash or a unique string out of another string is considered universally unique. Okay, so in that case, you're actually using the hashed version of a string to indicate at what position of the array you can find a certain value. Okay. Maybe a few more, other thoughts on other possible hash functions. Hopefully we get the idea, right? Length of the key, probably alphabetical, for example. But you might always come in or fall to the concept of collision. Okay, here we have another one. Okay, if going with alphabetical, is it possible to have a hash within a hash? Yes. So that's the other thing, right? You can have like a collision chain wherein your chain is actually also a hash. But the problem with that is even if you can make it unique, your problem will become storage. Because remember, going back to the analogy of what a hash function is, here the buyer and seller, in order to perform a hash function, you have to have another thing. In the case of buyer and seller, that would be the employee who knows what the index of a certain item is. That's why this is you can commonly see this in databases. When you say that you index your database, what you're actually doing is you're creating a hash table to refer a certain key as uniquely defined, so that you fetch it from the hash table rather than from the actual table. Okay, so yes, in the question earlier, if it was alphabetical, it's still possible to have a hash within a hash. But if you have a hash within a hash within a hash, then for every time you have some sort of list that you want to hash, you are creating a hash table out of it. So the problem there is storage. Okay. Any questions or any confusion so far with what was mentioned here so far? Okay. I'll leave you actually to think about it, like what's a good possible hash function. But again, it's something that has already been solved by other computer scientists, people way smarter than us. So if you are interested, try to read up on encryption, right? So that's essentially one application of hash functions. You want to create a unique value so that if I give another permutation of a string, the algorithm will produce a different output. Okay, so for example, for the case of apples, if I create an index apples and I hash it, it should produce a unique value. Now the counter to that is that what if there is another string that exists, not necessarily spelled as apples, but if I encrypt it, if I pass it through the algorithm that creates a quote hash, okay, it will actually receive the same value. Okay, and that's actually possible, right? So those are some things to think about, and if you have any thoughts on that, then let me know. Okay. Right. But any questions first with the idea of hash tables and hash functions? Okay, just to further the point, right? So if we had some code, let's say in Python, and we created our grocery list, okay, our grocery list, we can pass a key to it, right? So let's say here apples equals 80. This part, there's actually a lot of things already going on with this part. Okay, what it does is that it takes the key, okay, and then instead of simply storing it as apples, it actually stores a hash using a hash function. Okay, it stores a hashed version of apples so that in the array, your slots now become the hashed values. Right? So you can think of it as a linked list wherein 0 now is associated with, let's say, the hashed version of apples. So you have some transformation here, okay, that according to the encryption algorithm will create a unique value, so that even the theory at least, no, is that you cannot come up with another example that will come up with the same value and reserve that for slot 0. Same goes for avocado. If I hash out avocado, I pass it to an algorithm, making it so unique that whatever that hash value is becomes I know that that hash value will be associated with slot 1, for example. And it's not just a simple this one for 0 and this one for 1, but rather even you, for some hash functions, you even consider the index of the array. Right? Because remember, in arrays, if you know the index, then you already are operating at O of 1 in terms of fetching the piece of information. Okay. All right. Okay, so let's move to the next concept. But again, as mentioned here, this very simple piece of code already goes a long way when it comes to hash functions. Underneath this already performed the hash functions. You could also override this. We'll talk about some examples of hash functions, at least in terms of implementation, when we discuss NP completeness, and then assign a value to it. So a lot of things are already happening here, is what I'm trying to say. And the properties of whatever is happening there means that you already are reducing collision as much as possible because you have uniqueness, and it still attains the properties of O of 1 in terms of insert, search, and remove. Okay, but the downside, the main downside, will be in terms of storage, because you are still creating a separate sort of index. Simplest terms, you are creating extra pieces of information, the hashed version, for example, of the key, in order to just store a value to operate at this efficiency. All right. Another important, I think this will be the last, the last concept for this. So another important concept of hash will be the load factor. The load factor essentially is the number of occupied slots divided by the number of total slots in your hash table. This value is a simple ratio of how many slots are occupied over the total size of your array. So in this example, let's say in memory, you have values already occupied for index 1, 2, and 3. Then your load factor will be 3 over 4 or 0.75. Am I correct? Yeah, 0.75, right? So it dictates also when to resize the hash table. In most implementations, the recommended load factor is that if your load factor is greater than 80%, then you resize, it's time to resize. Sorry, this is a typo. It's time to resize your array. So you sort of have an idea that you're working with a dynamic array. Or if not, if you're working with a fixed array, then it means that the algorithm will search for some piece of memory that will fit the most optimal set of locations that are sort of side by side with one another. You often see this problem actually in games programming, but the idea there is that it's still optimal. You're using an array that is reallocated every time the load factor is greater than 0.8. Because as much as possible, you want to minimize the size of the array. You want to take up less memory. You want to make it more compact, right? And if you're saying that you have a large load factor because you have a lot of items already stored inside your array, then it's as if you're saying you are foreseeing that other items might be added, so you need a larger space to sort of add more hash items to it. Okay. So if you're doing research and you see the term load factor when it comes to a good hash function, this is simply dictating the number of slots occupied divided by the size of your hash table or the size of the array that you're working with. Okay, questions first about this? So the simplest implementation, as we've seen earlier, is a Python dictionary because you're using a key, you're creating a hash essentially. You're using the key as the index to a certain value. So you have apples, milk, and chicken. But for all we know, no, yung implementation niya sa ilalim is that it's creating a large hash table wherein it minimizes or it maximizes actually the load factor, and the values can be put to your hash table. Now, the reason why we discuss the hash table is because this will be the main data structure that we'll be using for our second discussion, which are graphs. Okay, so this one often has relation to the ever-popular Dijkstra's algorithm. Okay, but again, we'll split this discussion into two parts. This first part will talk about the fundamentals of graphs, so we have sort of a basic implementation, and then we'll extend it to something like Dijkstra's algorithm, wherein each edge has a certain weight. And I understand based on the on our project preparations, on our interviews, most of you are, or at least two of the groups will be implementing graphs in this case. So we'll first talk about graphs as a data structure, and then we'll talk about the breadth first search algorithm, or BFS for short, and then we'll take a look at a very simple implementation. Okay, so what do graphs sort of solve? Graphs often solve the shortest path problems, wherein the easiest the formula to sort of solve these types of problems is that first convert your problem to a graph. So we'll see how we'll do that programmatically, and then apply breadth first search. So it's still a searching algorithm. We're still looking for something based on some heuristic, but in the form of a graph. So what is a graph? At the simplest form, a graph is a data structure that models a set of connections. Okay, very simple. You have nodes, which are the elements, your items within your problem domain, and then they are connected via what's called an edge. So two nodes at the very least are connected using an edge. In this example, at least in face value, we say that A and B are neighbors regardless of direction. As you can see here, we have an arrow pointing to B. Okay, but irregardless of that, okay, so without minding the arrow yet, we say that A and B are neighbors because they are directly connected to each other. We also say that A and B are within the first degree neighbors from one another because they are directly connected to each other. Now, if I had another node C and B is connected to C, we say that B and C are first degree neighbors. So this is a first degree connection. Okay, but A and C are second degree neighbors or second degree connections. Okay, so this part, okay, is already considered a second degree. So what does this tell us in terms of how we might structure our data later on? This tells us that we can actually categorize our, relative to a certain node, how many x degrees of neighbors we might contain. For example, if I'm concerned with looking for all 6 degree neighbors relative to node A, then I know how many hops I need to consider a node as a 6 degree neighbor. Okay? These are very common properties of a graph: node, edge, the connection, and then how many degrees of connections we have. Okay? As long there's a path that exists between one node to another, you can measure the number of degrees or the number of hops one node might take towards another node. Now, from your CS105 or undergrad algo, you probably encountered also this, a directed versus an undirected graph. We say that a graph is directed if a graph is with a one-way relationship between two different nodes. Okay? So at this point, we consider the direction. We consider the arrowhead in this example. So we say if we are concerned with a directed graph, we are saying that B is A's neighbor. Okay, so A has a neighbor B, but B, okay, doesn't have a neighbor A. But A is not B's neighbor. Okay, because there is no arrow pointing to A. Unless we explicitly put an arrow from B to A. Then A becomes B's neighbor. But in this example, since the arrowhead is from A pointing towards B, we say that B is A's neighbor, coming from A going to B, okay, but A is not B's neighbor. Similarly, in an undirected graph, there is no specific direction as long as there is an association, or the relationship is bidirectional or mutual in this case. Okay. B is A's neighbor and A is B's neighbor. Okay. So there's no arrowhead. Okay. Now this will be important later on because it depends on how you would declare your graph to be in your own projects, right? If you declare your graph to be directed or undirected, there might be a different implementation for it. Okay, so for example, given a directed graph, okay, so now we can create our graph. We can represent our graph as a dictionary, wherein each key of the dictionary will be the will be the node reference. So in this case, A and B. Okay, using very simple terms so that later on when you translate it to your own problems, you can simply substitute it. Right? So we say that graph A, okay, index A rather, in a directed graph will have neighbor B. So now the way we can represent neighbors is by providing a list for that key. Okay, so the value of the graph, the value of a certain element in your graph in a directed manner will be a list. Okay. So we put B here. Okay. Let's label this as directed graph. Okay. Right. But for B, since you don't have any arrows pointing out of B in a directed graph, we still need to encode B inside our graph. But the value for B is an empty array. Because B has no neighbors. A is not a neighbor of B in a directed graph. Okay. All right. Clear so far? In this case. All right. Now what about the undirected graph? So in the undirected graph, B is a neighbor for A and A is a neighbor of B. Structurally, it's different. Okay, if we had an undirected graph, starting off with a simple dictionary, undirected graph A's neighbor will be a list containing B and vice versa. But notice that we are actually storing more stuff in an undirected graph because the relationship is mutual. The relationship is bidirectional. A will have a reference to B and B will have a reference to A, a direct first degree reference to A. Okay. So, what other things can we observe here? We can also observe that a node in the graph, okay, a node in the graph will also be, a node in the graph in a directed graph will be much shorter, or the information in the directed graph will be much shorter than information in an undirected graph because you have all sorts of combinations, and that the values of the neighbors for a given key is only for the first degree. Okay. It's a different situation if we're talking about the second, third, fourth degree. Okay. All right. Now, again, as another mental exercise, in the case, let's say we had the following directed graph. Okay, let's say we have C here. Okay. What is the problem if I had, let's just say that this is a directed graph, but we now have B to A. Okay, I have another connection from B to A, and then from B to C. Right? how will what can you say about the implementation of this directed graph if we were to sort of code this particular instance? Wait, sorry, I think I'm missing something. Okay, let's say we also have something like this. Yeah, from C to A. In terms of its application, let's say we are playing capture the flag, right? Where in one of the nodes, we don't know which one. Okay? One of the nodes contains the flag that we are looking for. Okay, if you were to implement this, what's one problem that you might encounter? And just let's say, for example's sake, you're starting with, let's see, this is the correct example. Okay. Let's just say you don't know where you're starting with, right? You could start with C, you could start with B, you could start with A, but essentially, if I start with A, and I look for the node that has my flag, it's captured the flag, right? Your three characters, one of you has the flag of the other. If you were to implement this, what's one problem for this that you have to consider if you're looking for that flag? Let's implement this actually so we can know what we're talking about. Okay, we still have directed graph. This time around we have B, so we're okay with A. But now for B, because I think I'm missing something here. For B, we have A and we have C. And then for C, we have A. Okay, that's correct. Sort of correct. C only. A only, rather. Okay, what can you observe about this? If let's say you're playing capture the flag. Okay, so Caleb says there's no sort of marking the visited nodes. It might experience an infinite loop. Okay, so almost, but I'm not sure about the infinite loop part, but why would you say that there's no sort of marking if we're playing capture the flag in this data structure? Gleb, care to share why that was your answer? Because the answer, but there was no sort. It will cycle A, B, C infinitely. A, B, C. No, not necessarily. So what you're saying is that from A, again, the idea is you have to start somewhere, right? So let's say you start from A. Okay? If I want to capture the flag, I'll have to go to B. Okay, let's simplify the problem. Let's say there's just one flag. I want to know who has the flag. Okay, if I search through A, and then I go to from A, if A doesn't have the flag, I'll go to B. If B doesn't have the flag, I'll go to C. Okay, but let's assume that one of them will always have the flag. At least one of them will have the flag, right? And try to connect it with what we implemented here, the graph that we implemented here. Okay, so that's almost in the sense that maybe you can expand on the first part of your answer when you said no sort of marking in the visited nodes. And if you take a look at the way the graph was implemented, okay, what would one potential problem be if you were searching for the flag? Okay, I realized where I was mixing. Okay, so in the case of order, okay, it really doesn't matter which order I can put my graphing model, so to speak, right? Because I can have the C index here first before the B index here. But just by observing this model, what are some properties that you can observe? If I search for the flag here, and then I search for the flag here, and then I search for the flag here as well, it had something to do with what you said earlier. No sort of marking on the visited nodes. Assuming if we start somewhere. Okay. Maybe to make it easier, let's say C has the flag. Okay, let's just say, for example, C has the flag. And given this implementation, if you start from somewhere, okay, and I look for a certain flag, what extra step will I be doing given the set of values that we established inside our implemented graph? Implemented directed graph. If there are two or more directions, so we have an answer. If there are two or more directions, how to decide which path to go? Okay, that's one. But let's say we, regardless of direction, we just go through everything based on these three lines that we implemented. What's sort of the obvious thing here? Obvious property.
Sir,
Yes.
can I make a guess?
Yeah, sure. Go ahead. Yeah.
So the problem might be I might visited a node twice.
Okay.
So let's say I started from A, so I'm searching for the flag for the C. So I
Okay.
might visited A twice or B.
Okay.
More than once, I mean.
More than once. Okay, yeah. So that's correct, right? So also with what Keb said, no sort of marking to explain the visited nodes, right? Because if we know that if for example the flag is already with C, okay, then it means that starting from A, I'll go to B. Okay, does B have the flag? No. So this time C will ask A. We know C has the flag. Okay, but it's like a anong game yun, what is that mobile game? Imposter something. So, yeah, so sino yung imposter, no? So C yung imposter. So C asks A, are you the imposter, no? But B, when it comes to B will again ask A, right? So there is that sort of extra step of processing. This should actually just happen with undirected graphs, but as we can see here, it can also happen with directed graphs. Because I already processed A, and I have, even if I process A, there might be a chance that I will process A again. So it's essentially a waste of time. That's why Kleb is also correct in saying that one possible problem is that there is no marking to indicate that I have visited this node already. And the reason I am stressing that out is because later on, when we talk about the graphing algorithms or even the solutions to problems for graphing, there will always be a section, a part of the solution rather, will be a checker to indicate if you visited that node already. Okay? So that's one thing to keep in mind. When solving problems for graphs, there will always be that avenue for writing a checker to indicate if if a node was already visited. Right? Right, good. Okay, let's move to the next word. Okay, any questions first so far? Clarifications? All right. So undirected graph, same thing, but now you have sort of that repetition. If you associate your neighbors with other points in the nodes. Now let's go to the breadth first search. So the breadth first search is essentially an algorithm that is applied to graphs and attempts to answer the following questions. A, is there a path from node A to node B? B, what is the shortest path from node A to node B? I think I skipped something here in the first slide. Yeah. So in this first slide, we see here the map of the JR line system in Japan. As you can see, you might have multiple stops if you want to reach a certain area. So let's say if I wanted to reach Tsuruga, for example, and I'm coming from Totori, then I could probably hop to Kinosaki Onsen, to Amanoshi Date, and then maybe I have a connecting line to Tsuruga. So that's like 4 hops. Okay? But I could also take like Chizu, go to Kunigori, Himeji, and then also go to Tsuruga. Okay, so both are actually almost, or this is actually much shorter, right? Because I have 1, 2, and then I'm there. But here I have 1, 2 hops. 1, 2. Is it the same? Oh yeah, it's the same. Okay, but there are multiple shortest paths towards a certain direction. Okay? So that's the idea of breadth first search. At least 50% of breadth first search. Given a certain starting point, you are attempting to get to your objective. You already know probably where your objective is, and you sort of want to determine what the shortest path is. Now, the second question that it attempts to, that was the second question. The first question is sort of the more common one. Is there a path that exists from node A to node B, from point A to point B? Okay. The breadth first search actually addresses both questions. The path that exists between node A to node B is also the shortest path. Okay, or in other words, if a path exists between node A to node B, then there will always be a shortest path that exists from node A to node B. So the breadth first search will always solve that problem. But in the case of a simple graph, okay, so let's take a look at a slightly larger example. You have node A, B, C, and D. Okay. If you are A, let's assume that you're starting with A, then it means that B, C, and D, and you are looking for something. Okay, again, we're speaking in very abstract manner because the problems that revolve around graphs sort of follow the same framework. Okay. B, C, and D contains something that you are looking for. BFS first checks if B is true, meaning if the something that you are looking for is in B. If not, the unique part about BFS is that it takes the neighbors of the not. Okay, so B is not. I don't have the thing I'm looking for in B. And the property of breadth first search is that if this is false, then it takes the neighbors, so in this case C, and then adds it to the list of search. Like list of things to search for. Okay. So in other words, it's possible that your list may continuously grow at some point, okay, as well as it might be an avenue for divide and conquer, because in this very simple example, we can see that if B is not, and according to our breadth first search description, wherein you look for the first degree neighbors, or rather all the friends of B or the neighbors of B, and then check them, we have a fork in the path. Now we go to D. Okay, so there is potential for that divide and conquer search. Okay, and we'll talk about those problems on Wednesday. But for now, we need to realize that the problem is that with breadth first search, you go to the next node relative from where you are, so A to B. If B is false, it doesn't contain the thing we're looking for, it's not our objective. The first step in breadth first search is to take the neighbors of the not and add it to your search queue. Okay. So we see how that's implemented in code later on. So what other data structure do we need in order to implement breadth first search aside from the graph model, the one that we did earlier? Well, the other data structure that we need is a queue. So a queue is a list-like data structure. It's an array where element access is done with only 2 operations, an in queue, which is to add something to the queue. But the way we add it to the queue is actually in reverse, right? Or no, not reverse, but towards a certain end. We can't insert something in the middle of the list. It either has to be at the top of the list or at the bottom of the list. Or in other words, to the left of the list or to the right of the list, if you want to read it horizontally. So a queue will only have 2 operations, enqueue and, sorry for the spelling, and the queue, which removes something from the queue. Okay. And as commonly known, there are 2 types of queue, first in, first out, and last in, first out. Okay, so simply put, if I add something to the queue and it's the first thing that I remove, then I'm performing a FIFO queue. If I put something in the queue and then that's the last thing that I actually inserted, that's the first thing I will evaluate if I perform a dequeue. So let's try to implement that in programming. So we have here a graph, ABCD, it's the same graph. So how will that look like in terms of our graph model? Well, we could easily put it in this case. A's neighbor is B because this is a directed graph. So A is equal to array list B, and then B is equal to C and D because it has different connections there. And then C and D are empty lists. Of course, very simple example, but it becomes more complicated if we have an actual graph. So let's implement BFS in this simple graph. Let's say our starting point is A. Okay. And then we'd like to, the thing that we're looking for is in F. Okay, we know that the thing that we're looking for is in F. So if we were to implement this graph and take note of the following directions, it would look something like the following. Okay. A equals BCH, B equals DF, C equals to EG, and D, E, F, G, H are sort of the endpoints of the graph. So they are currently empty. Now, how does breadth first search work? Well, the algorithm is pretty straightforward, and then we sort of evolve this to solve certain problems. We keep a queue containing the nodes to check. So we need a queue in the first place. Now, you don't have to implement a queue from scratch because other programming languages will have its own sort of native queue-like structure. You could implement it from scratch because basically it's just an array list. But you'll have to perform the queuing and dequeuing yourself if you want to use an array list. Okay? So the idea there is that you first examine, you pop a node off the queue, usually from the left or the first one inserted. So in most cases, BFS is implemented as a FIFO queue. The first thing that you insert in the queue is the first thing that you will pop off. And then you examine that thing that you just popped off. Is it good? And again, good is an abstract term again. It will depend on the thing that you're looking for. So we still need that function that examines if we are, if that's the thing that we're looking for. And then number 4 is the decision. If it's true, then you're done. You already found the thing that you're looking for. You're already in your objective. False, then we go to the same process we mentioned earlier. Add all their neighbors to the queue, and then you're essentially performing a loop. Okay, now take note, every time you're performing a loop, it is a candidate for divide and conquer algorithms. Okay, but for now, let's just stick with the loop. So you loop back. As long as there are contents in a queue, then you repeat the process. If the queue is empty, then it means that there are no good nodes, and the objective that you are looking for doesn't actually exist. Okay, so let's implement that. Okay, let's start off with a simple search function. Now this could be your search algorithm. I just called it search in this example. So I'll upload this after we code this. So BFS, let's call this BFS. So we have a function called search wherein we pass the index. So why do we need to pass the index? Because we want to determine what our starting point is. Going to the first graph, or going to the diagram here, then let's assume that we're starting off with A. So A will be the index that we pass to the BFS search method. Right? And then inside the function, we have a search queue. Okay, I'll call this thing search queue, which is a deck. A dequeue rather, not a deck. It's a dequeue. Okay, which is Python's native queue. I think I have to import something first. Let me just look that up quickly. Deck function. Just need to know the import statement. Okay. From collections import. Okay. So from other languages, it might be different. There we go. All right. So we search for something. We have a queue, and then from our search queue, we do something like the following. Okay, so what is graph? Well, graph is our search space. Okay, you could probably pass it in the function, but our graph is essentially our model. Okay. So the index being our key that we pass to our dictionary, we first add it to the queue. Okay. Why? Because we want to search for something, right? We are starting to search from ourselves, essentially. Right? Now, because of the problem we explained earlier, it's possible that in a directed graph, I might have nodes that I already visited that I should not evaluate again, because the graph might be like the earlier graph we had, right? We have a node that shares the same neighbors with other nodes. And if I pass through that neighbor again, the theory is I don't have to process it again. So one way to solve that is to create some sort of array that will hold all these searched nodes, or all the nodes that have already been evaluated. Okay, so how is that implemented? So the next part will be a while loop. And this part is saying that as long as there are items, true if there are items in the search queue. Okay. So as long as there are items in the queue, then continue to perform the loop. So we have that sort of main loop as part of our algorithm. Okay. Let's take out a letter, because in our slides we're dealing with letters. And let's pop left, okay, whatever we have from the queue. Okay, we are removing it to the queue so that we can examine that letter. This also means that we need a function. So here, before that function, we need to search first. Is this letter already processed in the searched array? Okay, so there are many ways to implement that. In Python, it's quite easy. We simply say if not letter inside the searched array, okay, then that's the time that we check. Okay, check if objective is found. Okay, here, this one is check if index, or if element is processed. You can change the variables around later on when I upload this, but ideally you want to name it after your problem domain. In this case, I'm just using letters. So we need to have a function that says if the letter is good. Okay. Now this is a very simple implementation. So let's just say that this definition is, okay, given some letter, if the letter is equal to f. Okay, because according to the graph, that's the one that contains our objective. Again, you can expand this to your own sort of problems. Then we know that it's good. We know that it's true. Okay? Then we say that we found a good letter. Format letter. Okay? And then we return true. Okay, because already found our objective. So naturally, our default is that we return false. Okay, we did not find what we were looking for. Now, there are a lot of things missing here that are more applicable to real-world problems. For example, if you were to trace the path, okay, then you would need to maintain some sort of array that would hold the different hops that you did before you resolve to true. Okay, so that's already something to think about. But again, we're just establishing the framework for this. Else, okay, our search queue will be appended with our graph letter. Okay, what is this saying? Remember, our search queue is the thing that we keep adding to it. Okay, so if we haven't found the letter, we add it to our search queue, and then we also append it to our list that, okay, we also append it to our list that has been processed. Okay. Why is it? Why is this why is it this way? What is this? What is this saying? Search queue plus equal graph letter. Okay, sorry, I tripped there a bit. But what is this saying? What are we actually adding to the queue? It's not the letter that we add to the queue, right? Because we already processed it. That's why we're adding it to the search array. But what are we adding here in this case? Adding the neighbor. Okay, correct. So adding the neighbors to the search queue. Because remember, in our graph, let's go back to the implementation, the value of graph at some index letter is equal to the neighbors of that graph. Okay? So, because according to our algorithm, if it is false, you add all the neighbors to the queue. So you add this to the given queue. All right. Okay, a few more things. I think we're done. Are we good? Okay, yeah. So I think I can copy paste this sample graph here. Okay. And then let's just run this directly. So let's say we are searching for A. Right? So we want to look for the node. We know that it is F. Okay? That contains the correct letter, right? Or that contains our objective. So we pass our starting point, okay? And then we expect that it will return the value, okay, for the value F in this case. Found good letter F, something like that. Okay, so running this will give us running this will give us will give us F. All right. All right. All right. Okay. Hang on, sorry. Mukha ko lang. Okay. All right. Okay, questions first about the implementation. Sorry, I had to fix some stuff. Okay. So this is a sort of bare bones of the BFS. We're using a breadth first search because we are starting from some index, and then the algorithm is we have a queue, okay, that keeps on adding because we are looking for each node exhaustively. Okay? And then if we don't find what we're looking for, we add the neighbors of that index. Okay? All right. So what is the analysis in this typical graph? Let's go back to the slides. So to end that implementation, right? The runtime analysis is that for searching the entire network, at worst, it will take O of n, where n is the number of edges in the graph. Okay? Why? Because the number of hops, essentially, to look for, if you're going to pass through all the nodes, then the number of nodes is O of n. Okay? Adding a node to the queue takes constant time because you just insert something to the queue, first in, first out. So it's due to the hash table because we're making use of a hash table to represent the graph. Doing it for every node, however, will be at worst O of n, where n is the number of nodes. Okay? So therefore, breadth first search by default is O of n plus e, where n is the number of nodes and e is the number of edges. Okay, at least in terms of runtime analysis. Okay? So, any questions first about this implementation? Clarity. So I'll upload this to Canvas later on after this class. And what I like you to do for now is to just study the structure so that when we discuss the problems on Wednesday, okay, that involves graphs, then you sort of know the different properties of breadth first search. Okay, wherein if false, add the neighbors. If true, then you're done. Okay. At the same time, one good practice for this is to what if you wanted to maintain the paths? So that's one exercise that you could do. I'm not requiring you to do it, but if you want to practice graph, and this might appear in the problem set, right? If you want to practice graph traversal, then how can you modify this program so that it keeps track of the path that was taken relative to index? Okay, you could try it with a larger graph, draw it first. So the usual practice for this is draw the directed graph, set it up using hash tables. Okay. Just pick one as a decision function. Okay. Have a mechanism to determine if something is already searched. And then try to insert a way to keep track of the different hops that occurred as you search for your objective. Okay. And one tip there is that most likely for a given entry point, let's say A, your structure should hold multiple paths. So it's actually an array of paths as a data structure. Okay. All right, so I'll stop there. Any questions so far about the basics of graphs? Clarifications. Okay, so I think I'll end here first. So again, for those who haven't signed up yet for the first checkpoint, you can sign up within the week. For those who are who are already in the second checkpoint, you can also schedule something within the week if you already have something that you can show. Again, the different groups will have different notes based on what we have discussed and your own problems. And for this week, we'll have a asynchronous session on Wednesday and then problem set on Thursday. Okay. All right, questions? All right. Okay. So if there are no more questions, I think it's almost dinner time for some of us. So that's it for today, and I'll see everyone on Wednesday, at least virtually via the asynchronous session. If you have any questions, please don't hesitate to email me or via Discord. Okay. All right. Thank you, everyone, and see you next time.
Thank you, sir.
Thank you. Stop recording.